All right. I'm sure say this is up and running because there you go. All right. So we're good now. Okay. So yeah. So as we say now, the question is how we use this formula. Now I'm going to scroll down and show you what exactly is happening here. All right. And for those of you not used to this triangle thing, um, here's a closer look. This it's a bit blurry though. It's a bit blurry. Uh, hold on a sec. Isn't there a better version of this image? All right, guess not. All right. Okay, so remember that this is the formula we use to calculate specific heat capacity, and so based on how this one is written, let's change the color here. A little bit darker here. All right, so we just part of these because well that's how we use the triangle. And notice the hand in this diagram or in this triangle, this formula. This hand is covering specific heat capacity, which means that the rest of the triangle is telling you what to do. It's saying that once you know the energy, right, that's measured in joules, you're gonna actually divide it by the product of the mass and the temperature change. So we're gonna go through the results that we got. All right, go through the results that we get and see where we can find all of this information. Right, temperature change and the mass, right, and the heat energy transferred. Right, so all of that will give us the specific heat capacity. And remember that a couple things to point out here is that the symbol used for specific heat capacity here, the small c. So, right, it is actually represented by a small c. All right, and notice that's represented. That's not telling you what the unit is. What it is measured in is something different. All right, so then the information would be here that specific heat capacity is measured in units, right? And the units are actually referred to as here, joules per kilogram per with degrees Celsius. Our persons more write it like this, J, kg, and today, let's see. All right, so there you go. All right, guys. So, any questions here?
No, sir.
No.
All right. So then, because if we decide to go through some past papers, very common 1 mark questions. Like what is specific heat capacity? State the units of it. State the symbol, and also distinguish between specific heat capacity and there's also something known as heat capacity, which is represented by a big C. So that's something we will look at as well. As a matter of fact, the discussion questions for this lab are actually not the ones that I had originally planned, but I think this lab was a step down version of a CAPE lab. So it's some of the questions were missing. So usually the CXC labs have more questions because they're trying to get more knowledge out of you guys. So I'm gonna expand this one. But so just remember that the formula so far, just pay attention to the formula here. All right. How we use the formula. And of course, this concept of specific heat capacity. Last class we did the definition of it. So if we go back to that part, well, okay. You were asked to distinguish between heat and temperature. So we did that. What's the definition for specific heat capacity was given somewhere. Was it here? Yeah, it is. Definition is here as well. So, this is something that we need to know for exams. Let me just and maybe just send the stream link because some persons seem like they're unable to join due to internet problems. Maybe YouTube might work out better for them.
Sir, you work a little better on small devices like phone or tablet, sir. In the computer like Jot, whole upper internet, sir. Now I
Oh,
realized,
so
yes,
so
sir, because I actually tested out and I realized that it was unstable on computer. Because it would kick me out on computer sometime, but when I used it on phone, it was, and sometimes it's blurry on computer, but when I use it on phone, it's okay.
Oh, okay. And that's for Zoom or for YouTube.
Zoom, sir. Like
Oh.
it's probably the resolution draws more.
Hmm. I was wondering though, when I was using StreamYard, anybody tried StreamYard with their phone? Because when I use the StreamYard, um, I think that
Okay.
never tried. Okay. All right. Well. All right. Well. So that it is then. So let's see then. Let's see how we can help the persons then. Where is the physics group for this one? Because can't seem to find it. So many groups around here. Uh, oh, here it is. All right. Mm. And then like some persons don't realize that we use the same link. All right. Send this again because some persons just don't get it. All right. Anyway, so definition here for specific heat capacity certainly is vital here for us. All right. So now let's go through the objective here of this lab here. Didn't put the skill up top there. The skill for this lab is actually it's gonna be, and then let's put last class date would have been the 21st. It would be the 21st of the fourth. So yeah, I think I got I think I started doing said me I start at this lab. Or skill is actually here. AI is a skill, so and whatever lab number that you should have there, put that there. I don't quite remember which number, but certainly. All right, and then this will go down as one of the compulsory labs. So, but we have this information here, guys, from last class. We're gonna use this and try to calculate the specific heat capacity of copper. Now, here's a concept now that students I would say they might struggle with at first, but then it once they spend time with it, they get it. But this one no. And I'm going to remove metal one and just put copper because it's actually we're just going to focus on copper and just remove this. All right. I guess all of this can remove as well. All right. So there we have all of this space to work out this. All right. So let's go, guys. So here's the assumption here, guys. The assumption that change in the temperature of the water. Remember, if we go back to the experiment, we heated the metal, all right, in water up to 99 degrees or somewhere there about. Let's go back to the table and see what happened there. And let's recap what happened. The metal initially, and this is when we heated the metal here. And if you guys remember, this 98.6 degrees Celsius here was the temperature of the metal. So one of the first things we need to understand with this formula is that in the symbols here, mm represents the mass of metal. All right. So in physics, we tend to write some subscripts here, especially when you're using formula. But cm and small c, as we say, specific heat capacity. Let's write SHC for that one, and of metal. This is what we're trying to find. All right. And also delta T triangle means what? Anybody remember what the triangle mean?
Change.
Yeah, very good. Change in. So change in temperature. And this is something that, and this all of this side is for the metal. All right, all of this side is for the metal. So what this is saying is that we need to use this formula for each of the substances that we have in the lab. So all of here is for the metal. And because the metal was heated and all of that, not only was the metal heated, but the water was heated. So the W here stands for water. So if we change the color here and highlight that, this part here is the mass of water. All right, this part here is the specific heat capacity. Of water. And then of course, the triangle T there is the temperature change of water. All right, so all right. All right, so hope everybody's seeing what's happening here. All right, we are using the formula 3 times. All right, why? Because we're using it for 3 different substances that were heated. Remember, the metal was heated, and then we transfer the metal to the water in the calorimeter. So if we should go back to the image of that, all right, and of course, calorimeter is common name for that. I'm trying to see if I can replicate what happened in that experiment. All right, so all of these versions here have electrical things, but so there's actually an electrical version to this lab as well, but not fun. I'm not a fan of it really. Well, nothing is really wrong with it. It's just that it takes a different approach to it. And let's see, immersion method they call it. And all right, let's see. All right, no, they be I don't like these images at all. These images are just so so off. All right. Never mind that. And never mind that. Let's specify method of mixtures then. See if we can find something. Yeah, definitely find something here. All right, so meanwhile, we that comes up. This now we're trying to show here with the water. All right. So when we put the heated metal into the water from the previous lab, the heat from the metal was transferred to the water, causing the temperature to rise. Right. And no persons really do remember these stuff. So let me just go back to trying to get back to the lab, because there's somebody say them last and them do understand. Which the lab is actually on YouTube, so you can look up the lab. And it's oh, there it is. All right, this is the mass of the water, as we said right here. Let's just part this off. Remember using that same formula 3 times, so that's for the water. Now C, MC, CC, delta T, C. The C here stands for the calorimeter. Let's use a different color now to highlight that. This, yeah, probably use a blue there or something like that. All of this here is for the calorimeter. I don't know why this writing so large. Can I change the font size for this one? Yeah, certainly, probably. Yeah, I'm gonna reduce it to that. All right, so here is the calorimeter. All right, now you might be wondering, so what is a calorimeter? All right, calorie means heat, meter means measure. So it's a device used to measure heat in the lab. All right, usually, well, it can be. All right. Usually, it's a device that that prevents heat from escaping. All right, because with the calorimeter, a calorimeter could be like a styrofoam cup, for example. All right, and we know that we use a styrofoam cup to like put like soup in and like tea, and so anybody knows why we put the tea or the soup in styrofoam cup and not in a plastic cup? Yeah.
Sir, because it will keep it warm.
Yeah, but how does it keep it warm? That sounds like something where your mother tell you, or something where you learn as a child growing up. But how does it keep it warm?
It has different layers.
Oh, the styrofoam cup has different layers. There's different layers. Interesting. Let's bring up an image of that. So these are the questions they'll ask you in CXC. You know, those are what they would pack questions with to get some marks, because you explain here. Everybody seeing the image on the screen here?
Yes, sir.
All right. So the key here is why is styrofoam used, right, to keep hot liquids? Well, there's a short answer, there's a long answer. The short answer is that the styrofoam is an insulator. Now, does anybody know what an insulator is?
Insulator, a current can pass through, sir. Or something can pass through. Like heat or something can pass.
Heat can pass through?
Insulator, sir.
When you're saying heat can pass through an insulator?
No, sir, I said it can't. Sir, don't bother, sir.
Oh, okay, yeah, definitely. That is the correct statement. All right, so yeah, I hope everybody heard that statement from Jenner, because yeah, it's definitely an insulator is a material that prevents the transfer of heat from one part of the material to the other. So on one side, all right, so on one side, it's hot, and the other side is cold. So why is that? The heat will move from a hotter object to a colder object, but then this now, styrofoam, all right, styrofoam is an insulator, and that means that it prevents that. So insulator is that's what's happening here. All right, so that's what's happening. All right, the insulator is like a block, so almost like a blocker, almost like a bouncer at a party. Anybody know who a bouncer is?
Bouncer.
They're
Yeah.
like a security.
Yeah, like security. Very good. So it's like this material and the heat would be like the people, whole heap of people outside want to go into the party, but then you have like two thick men at the doorway. All right. So imagine that this styrofoam is the doorway. All right, and then them basically block, they block the way. So that's what styrofoam does to heat. All right. Styrofoam can block heat. So no, notice that if they but then when you're drinking tea or soup from it, it doesn't the cup still feel, doesn't it feel hot sometimes? Just the same.
Yes, sir.
Yeah, so then it has its limits. And then remember this, that when you buy it at a little store, a little restaurant, you know,
It's not really all that hot, sir, but it
mhm.
depends on how much heat is applied, sir. Like if too much heat there, then you're going to start to feel it, sir. More heat, more.
Yeah, definitely. Definitely. The hotter it is the more likely, it's more of it you're going to feel on the other side. All right, so that's
Yes,
true.
sir, but you know usually all that hot, but you can feel a little heat that come out.
Yeah. That's the idea there. That's certainly the idea. So it reduces the heat loss. But then what we're learning in this experiment is that you can't prevent 100% of the heat from passing through. So even though the bunk size is big, and him take up the doorway space, if there are too many persons there, people can probably squeeze through, because by the time I'm parting off a few here, maybe a short one probably go through them legs or so, especially if they are tall. A lot of them are tall. Or you can go around them. And you're going to always have that odd one that make them way into the party, you know. Um, so that's just what it is. But then you guys probably can't relate to that now because it's COVID, and then we're not allowed to have those type of events. But you can use your imagination, So here is the situation, right? So the styrofoam cup is an insulator, and in the lab, you know, it's actually referred to as a calorimeter in that case, because once we put a thermometer in a styrofoam cup and we close the styrofoam cup, it becomes a calorimeter. All right. So as I think it was Giovanni that was saying, different layers are in the material, and that's what the calorimeter is. The calorimeter is like a styrofoam cup on steroids. So let us compare the styrofoam cup, because if we're doing this at school, face to face, it most likely would use a styrofoam cup. But we do have a calorimeter, but so you would have seen it in the experiment last class, what the calorimeter looks like. Calorimeter almost look like it have layers like a thermos. So almost stay like a thermos. So that's how it really works here. All right, not seeing the okay. Well, let's show you this then, because the styrofoam cup is just a step down version. Let's give me a new slide here and show you this now. All right. And so this would be inside of it. Everybody seeing this?
Yes, sir.
Yes, sir.
All right. So now let's just zoom in. We really don't need to see the top here, but yeah. So this is like inside of it. Really, it's So this would be like the water here. So the idea of it is that it reduces the heat loss, so the heat can't really pass through. The other thing that the styrofoam, the other thing that the styrofoam cup don't have is a metal layer, shiny metal layer on the outside. All right. The idea is that you can get extra insulation. You can get extra insulation from metals, shiny metals, by the way. It's you might be thinking, oh, but aren't metals good conductors of heat? And they are, but just remember that there are 3 ways in which heat can be transferred from an object. So that's something that's huge on the CXC syllabus, the ways in which heat can be transferred. So so yeah, shiny objects, and in the case of a metal, yeah, does conduct heat, but conduction is just one method of heat transfer. The other 2 is what? Anybody know the other methods where heat can be transferred?
Is it convection or radiation?
Conduction.
Well, yeah. All right, so I'm hearing some responses here, which seem correct. Shanta is saying convection and radiation. So we need to write down that because one of the questions in the lab will ask for that information. So heat is transferred by, and this is conduction. All right, that's by metals, right? And good conductors. And you have convection, which is by liquids and gases. And also we have radiation, which is through anything really. What the shiny object does is prevent the heat loss by radiation. So a shiny object is an insulator for radiation. All right, so that's why the car, for example, most cars are shiny, if not all. If it's not shiny, maybe it hasn't been sprayed, or probably it old or something, but the outside of cars should be shiny, and that prevents that the radiation from reaching persons inside the car. So even though when you touch the car on a hot day, yes, the car going to feel hot, but it should be a lot hotter. If it ever had the paint on it, or the sheen on it, then it would be much hotter. As a matter of fact, to be so hot that you probably could just use it as a stove. So that's the idea there. But certainly radiation. All right, so through metals, heat transfer by metals. So heat, let me just write that down here. Heat transferred by metals. And by metals. All right, so what we have here, convection, that's heat transferred, all right, by what? Liquids and gases. So when we're designing a material that's an insulator, meaning that we don't want any heat to pass from one side of it to the other, we have to prepare for all of these 3 methods. So the foam now takes care of 2, takes care of the conduction, because, well, there's no metal, so there you go. So it won't be conducted. Convection, no, it does to a point. Because, well, it's heat transferred by liquids and gases. So you with your soup or your tea in the styrofoam cup. All right, so there's really steam as well inside there, and there's a very hot liquid, and maybe and then these particles are smaller than the holes in the styrofoam, so maybe some of them can pass through on a very small scale. All right. However, radiation now is something that you can't prevent now, because what you're feeling on the outside of the styrofoam cup is, in fact, the radiation, the radiated heat from the hotness inside of inside of the cup. So, and what I'm explaining for the styrofoam cup is the same thing for the calorimeter. All right, so remember that the design of it, the only thing that the calorimeter would add to this now is the radiation protection. All right, so heat transferred by well by all matter really, and and also empty space. So radiation is really hard to prevent. You know, every day we are even exposed to radiation, even if we're wearing suits, body suits, and so like we in a nuclear environment, we still will be exposed to some radiation. Might be a lot less with the suit, but certainly can't prevent radiation, guys. And so radiation is one of those things here. So we try to, so the calorimeter adds the layer of the metal now to further prevent the heat loss. So that's how it works. All right. So I hope by now you would have a slight idea of how the calorimeter work. Right? Because once you understand the principle now, we know why we have to use it in this experiment. Let's go to the, yeah. So calorimeter, because of that now, because it's not 100%, guys, we have to factor it into this lab here. So therefore, we need to know the mass of the calorimeter. We need to know the specific heat capacity of the calorimeter. And we also need to know the that the temperature change that it goes through. All right. So then this would bring me to another thing though where you need for this lab. All right. See how much concept this lab really teaches, well, tries to teach you really. All right. Laws of heat transfer. And then so we have 3 methods of heat transfer, but check this out. We also have 3 laws of heat transfer. And the funny thing about the laws of heat transfer is that we start from 0 and not 1. It's actually 0, 1, and 2. So that's the beauty of this one. All right. So well, the first law of heat transfer still actually states that heat travels from as a matter of fact, let's just get into the nitty-gritty here. All right, when the laws really states that, and at SHC level they don't really pressure, but one of them is that heat will always flow from a hotter object, right, to a colder one. All right, so let this sort now, guys. Right, heat will always flow from a hotter object to a colder one. All right, now that's it. Direction there. Any questions there? All right, check this out. This is incomplete now. There's more to be added. Until both objects are both, let's put both are all, if it's more than 2, and say objects reach the same temperature. All right. Has anybody seen this law before?
Yes, sir.
No?
Yes, sir.
You've seen it? All right, Chante. Well done. All right. So that's the principle here. What we mean by hotter object? Hotter object mean
Greater heat.
if you want to look at it that way, let's check this out. Higher temperature. Object that have a higher temperature, that's the hotter object. All right. Cooler one mean lower temperature. So sometimes some books will refer to it as a temperature gradient. All right. So once there's a difference between the temperature of two objects, then heat will flow from the one that has a higher one to the one that has a lower one. Everybody understand that? It's nature's way of balancing things, right? So that's how heat behave, but unfortunately, that's not how persons in society behave with their money. Persons who have a lot of money, they tend to they tend to do what with it? Do they freely give it?
No, sir, they mean with it.
Yeah, that's the situation there. And I want to tell you, you could argue that they're not mean. Persons who have a lot of money do spend a lot of money. The money somehow doesn't reach the hands of, well, probably don't reach your hands, certainly don't reach mine.
Sir, they spend money for foolishness, sir. Like, say, like one Leonardo da Vinci would have painted something, sir, and they would have paid 300 million just one painting, just one man to paint something, sir. But all look, right. Funny poor did it, sir. Hey, look, funny poor, they're not spending for him.
Well, there you go. But it's a value. It's a value of it still. But you're not looking at now, generally, and this is the same thing if we can apply it to the concept of heat. All right. If you're in a room right now, guys, there is one, and all right, somebody send a message here in the group. Okay. So yeah. Yes, January. It will be all right, not January, it's actually Jonathan. I've seen a message in the group here. Jonathan is there. Yeah. Jonathan, if you're hearing me, this would be posted in the classroom. Yeah. All right. So yeah, so that's the concept here, guys. You just but I'm saying if you are in a room that has a light bulb and then so the light bulb is hotter than everything else in the room. You're watching TV or you're doing whatever in the room. The hottest object in the room is usually the light bulb. Everybody agree with that? You have anything? You have anything hotter than the light bulb that in the room now? Because right now in this room,
the fridge box.
Come on. We're not talking about the kitchen. We're talking about a bedroom or a living room.
And let's say orange boat them, sir. A hot man.
Right. So there is it. So that heat to be transferred to everything now. Why you going to feel hot? Is that the temperature? Again, there's a temperature difference, and so the heat will travel to you, and which is the case happening to me now. I have like lights here. Heat leaving it, and then it's going to reach you, and then because your body is feeling that heat now, your body responds to cool itself down and start sweat. So then that's here the principle of heat transfer here. So that is one, as we said, this is one important law of heat transfer. And as I said, the heat travels from an object of a higher temperature to one of a lower temperature. All right. Until everything reaches the same temperature. So that's the idea. All right. Everybody good with this one?
Yes, sir.
All right. Of course, the other definition though. I don't want to. The other law would say that it is impossible to reach absolute zero. So what it means is that the coldest temperature you can get is, well, you can't reach a stage where there's no heat in an object. That's what the other law says, really. All right. Well, let's go. Won't want to stray too much into that because the lab really is focusing on this law here. All right, so heat will transfer between two objects until them reach the same temperature. So with this experiment now, we have a lot of temperature change to account for, and hence that's why we're using this formula 3 times. All right, so remember one for the metal, and then one for the water, and then one for the calorimeter. All right, and that's it. Now, the catch is that for the metal, we actually have an unknown here. As a matter of fact, there's also another unknown that I should find out, and I think we have to bring up the data for the the specific heat capacity. I think we're missing on something. The specific heat capacity of the, yeah, there it is. All right, I want to copy some information from this, and I should have really alluded to this here. This actually showing you what happened in the lab here. All right, and some screenshots there. All right, this now is what we need to capture, this information. So let's zoom in. Let's zoom in and pick it out. All right, so them give you the information here for the this looks to be the specific capacity of water, which is 4186. This is very popular information in CXE exams. So let's put it here on the screen here. They have CW there. Actually specific capacity of water here. So what I'm gonna do here is add that. All right, this is the specific heat capacity of water all the time, guys. 4186. All right, joules per kilogram per degree Celsius. All right, so this is a constant. All right, once we're talking about water, this is the amount of heat water can hold. All right, before temperature changes. 4,186 joules of heat energy it absorbed before you say a 1 degree change in the temperature. Now, how much is 4186 joules in real life? All right, let me show you this now. You know that when you exercise, them say you burn off something, right? But everybody know the word that refers to what we burn off when we exercise.
Sir, calories.
Calories. Okay, well done, Ashanti. Well done. Yeah, definitely. Calories is that word here. But where are those calories found in the body? Right. It's a question. Where are those calories found? Where does your body store calories? No. So nobody knows that one? Body store calorie. Try underneath your skin. And that's where it's stored, underneath your skin. That's where calories are stored. All right. For those of you who do biology, your skin has layers, and so, and they function. Yeah.
So I'm not the biology, but no, but epidermis and dermis.
Yeah. Yeah. So the space between the skeleton and the skin and the outside skin, that's where it is stored. All of this is what you're feeling. Some of you probably feeling pure bone because you don't have much between it. But that's okay. Not all of us can be fat like me. You understand? So but then the so-called fat is actually referring to calories. So it's calories there. Your body just basically put it there for two reasons. One, as a source of energy when time you're not eating any food. It has something to, or maybe you eat too much food and the body say, you know what? Well, we don't really need all of this energy, so we just store it though, and then it becomes layer underneath your skin. And so you put on this COVID weight now and all this thing. But that will soon go. But just remember that then to burn off that fat now, whoa, that's gonna take some doing though for some persons. When you're young, it's easy. And when you're old now, it's a little bit harder. But 4,186 joules, that is like how should I put that now? We have to multiply this to convert it into calories. We have to 4.186 calories equal to 1 joule. So would actually divide this by 4.1. Actually, all right. So that's like doing. It takes about 3,500 calories to lose a pound of those of that body weight. 3,500. So would have to go multiply this in. Well, that's a lot though. Just know say it's a lot. But this constant is important though. It never does speak out of thin air. This was actually calculated by the first scientist here. I think it wasn't Joule though. It was James Joules. But all right, so this one, the calorimeter here now is the same thing. The specific heat capacity of the calorimeter here is gonna be, let's go back to that image, guys. And that's the thing, we're out of time, but let me just find the data and so we can put it in. See there, it's actually CC here. That's what, 386? I know, 387. All right, so we're going to copy this. All right, and then drop it here. It's going to be 387. Let's drop that here. 387. So if you look at this number, 387 and 4,186, you obviously realize that one is bigger. 387 joules per kilogram per Kelvin. So our degrees Celsius. So this number here is a lot bigger for water. And they're going to carry us to some other stuff about water. All right, guys. So any questions here?
No, sir.
All right. So this is unknown. That's what we're going to find. All right. So we'll take them now piece by piece now. We're going to drop some columns now. As we say, and we're going to separate them. Share them. Separate them. And then what we're going to do is put in the numbers for each of them and work them out. So the mass of the metal now. But I have to go in the data and find all of that. All right, guys. Just give me a couple more minutes to finish this and we get this up here. All right. So now we're seeing here in the table mass of metal, all right, which is 8.9 grams. All right, let's put in the symbols here. This is our mm. Mass of water is mw. Mass of calorimeter is mc. All right. All right, initial temperature of water. All right, so let's call that delta T and W. All right, final temperature of water. Or not, let's just call this T1 then because we have delta is subtracting here. So let's just put T1. TW and let's call that 1. And of course, the temperature of water 2, that's the final temperature. Initial temperature of metal, of course, we're going to say TC with it'll be 1. All right. So just remember I use 1 for initial and 2 for final. And that's where we're going to find the temperature change, guys. Which this probably is the easiest part because it's 1 temperature we have to work with here for everything. All right. So remember now for the metal, let's put the temperature change here, guys. Temperature change. If we go to the metal, initial temperature of the metal was what? It's 98.6. All right, 98.6. So it's going to be 98.6. But then the final temperature of the metal is the same as the final temperature of the water. All right, why? Because the metal goes into the water and it was covered, right? And the rule for heat transfer says that heat will transfer between what? 2 objects until they reach the same temperature. All right, so that's the important thing. So the metal will lose all the heat it have until the water and the metal reach the same temperature, guys. That's why it's called the method of mixtures. Them mix together until they reach the same state. So this is 20 degrees there for that temperature. All right, this is 20 degrees there. Hope everybody's seeing what's happening there. This is for the metal. Metal goes in at 98 and cools down to 20. As a matter of fact, I should switch these around because the formula here, and I'm going to point out this to you guys. Temperature change, or delta T, is equal to the final temperature minus the initial temperature. So then that's that. All right, so that's the concept there, guys. So I forgot what's up this thing here. All right, so we're going to switch this around then. All right. So, any questions here, guys?
No, sir.
All right, so we have 20 minus 98.6 for the temperature change. Remember that this is for the metal part of that there. All right, remember that the specific heat capacity of the metal is unknown. We're multiplying it by an unknown, and the mass of the metal, we can carry that down here into this question. Let's just take out that part. Yeah, there we go. And can remove that too. All right, so we're just going to put CM here. Let's carry that down, CM. And then now the mass of the metal going back to this would be what, 8.9. So 8.9 will be there. So if you use a calculator, I suppose you can get a half an answer here really, because we still don't know CM, which is what we're trying to find here. All right. But when you take away 98.6 from 20, you're supposed to get a number. All right. And that's the number we're interested in. All right. Remember that all of that would be equal to what's happening over here. So when drop this here, mass of water. Mass of the water, go back to this. Mass of the water here is 69.93. And so we have here. So we have 60. All right, so it's gonna be 69.93 and times this number here, 4186. We just say that this is the specific capacity of water. All right, so 4186. Temperature change of the water now. How much did it change by? Going back here, water was initially at 19.7. The final temperature of the water was 20.6 after it absorbed it from the metal. All right, so what's the difference between 19.7 and 20.6? All right, so it will be 20.6 minus 19.7. All right, so this is what we're multiply. All of these three numbers we're going to multiply, guys. Any questions? All right.
No, sir.
All right, so that means I can calculate this. Well, you guys do that after class then. So as you're probably having problems there. All right, let's move this now. All right, this now, we use the blue for this one now. So we're going over to the calorimeter now. We're going to set out everything that we need. And you guys, you seem like you can manage on your own because you're not saying anything. So, all right, so the temperature change of the calorimeter now is the same as the water because the water is in the calorimeter. So remember that the water and the calorimeter will have the same temperature. So the temperature change will be the same here. It will be the 20. All right, it would be the 19.7, which is the initial temperature of the water. Initial temperature here, TW there. And then final temperature was 20.6. So same thing. So it's going to be the same 20.6, which is the final temperature. Remember, going back to this equation here, temperature change is final minus initial. Final temperature would be 20.6. We're taking away 19.7 from that. All right. Of course, this is the specific capacity of the calorimeter. The mass of the calorimeter is given here as 39.53. All right, so 39.53. All right, so this is what we're going to multiply together. 39.53 times 387 times the difference here between 20.6 and 19.7. And up to now, nobody finds a total. So you guys will have a nice time with that one. All right. So that is it. So we're getting somewhere. All you need to do is multiply the numbers you're seeing here. All right. And then you'll get your answer. And this is where most of the marks for this lab coming from. All right. So,
Yes, sir.
yes. Question?
No, sir, I just saying yes.
Okay. All right. Let's just move this over here. All right. Yeah. So get some space there. All right. So, yeah. So that's it, guys. Now, this could tell you the answer you're supposed to get. You're going to finish up that. And then let me know what answer you get. Also, and that's the thermodynamic principles apply to the method of mixtures using this experiment. All right, that is also here. So the answer for C is actually given. Laws of heat transfer. All right, this is it. This one, no. Yeah, that's actually the 0th law of thermodynamics, if memory serves me correctly. So so you can actually look up that for extra reading though.
Yes, sir.
All right. So that's it. All right, guys. So I'll send this in the group. Probably we don't need this diagram. Can't take out that. All right. So I'll send this in the group, and you guys finish this lab. And if you have any questions, you ask. All right. So let me export this, and you get it. And the reason why I spend so long with this lab now is that, as we say, we we're teaching the concept that the exam will ask from it. All right. And today is what, April 22. Continued. All right. So that's what we're doing here. All right. All right, this should be not chemistry, but physics. Let's put that in the physics folder. And we're saving it. All right. So in a few seconds now, this will be transferred into the group. All right. And then you're gonna let me know if you see it. All right. So
This is lab number how much, sir?
no, it should be lab 7. All right. Yep, should be lab 7.
Yes, sir.
Dwayne, you keeping track of the labs them?
Yes, sir.
This is lab 7, confirming.
No, sir. 6.
Lab 6. Oh, so
Yes, sir.
lab 6. Okay, so lab 7 for it's for, it will be for Jonathan then. Jonathan is there, so it will be lab 7 for him. Or if he's keeping track. All right.
Yes, sir.
All right. So yeah, so that's it. So as we say, guys, you have to finish up the calculation. All you need is your calculator, put in the numbers, get your answer, and then you do the substitution. All right. As we say, if you have any questions, you use the group to do that. All right. And I'm hoping that you're seeing this in the group. Let me just send it.
Yes, sir.
All right. Let me just send it into the other group as well. So Jonathan should be able to see it as well. And all right. So yeah, it's there. All right. So as we say, any questions, you just show me in the WhatsApp. All right. As well as you can ask it under the YouTube video as well. You can ask the question there because I'll see those as well. So anyway, any method that work for you? All right, guys.
Yes, sir.
All right. So I'll see you guys next class. All right. So